In this presentation, we're going to look at a worked example from the uniform distribution, particularly the continuous uniform distribution. So this is a subway example. It's a straightforward enough example. The uniform distribution is commonly encountered in computer science applications. It's well worth knowing about, but also it's actually a very good use case to sort of introduce people who are new to probability distributions, particularly continuous probability distributions, just to get them used to the bare basics of it. And so that's why we'll sort of look at a sort of generic worked example that will go along with that use case, just to sort of practice probability distributions. Anyway, suppose there's a platform in a subway station in a large city, which might mean Tokyo. Anyway, subway trains arrive every 3 minutes. Now let's just sort of assume that's almost systematic for the whole day. Okay. What is the shortest possible time a passenger will have to wait for a train? What is the longest possible time that a passenger will have to wait for a train? What is the probability that they'd have to wait longer than 2 minutes? And what is the probability that they would have to wait less than 45 seconds, i.e. 0.75 minutes? Just for the sake of clarity, what we're going to do is we're going to work in terms of minutes, just to keep it simple, but we are working on the case where we could have fractions of minutes, okay? So we could otherwise work in seconds, but we'll just, for the sake of consistency throughout, we will just work in minutes, but we could have fractions of minutes, like 0.5 minutes or 0.36 minutes, so on. What is the expected value and the variance of x? Okay, so part A and part B, what is the shortest possible time a passenger will have to wait for a train? So if the passenger arrives just before the doors close, they just walk up exactly before it's about to take off, perfect. The waiting time is 0. So what we would say here is A equals 0 minutes. Now, what do I mean by A? So essentially the way we would write a uniform random variable called x is we would sort of say U, where the parameters are A and B. A is the minimum value, B is the largest value, maximum value. So essentially x can take any value with equal probability, equal likelihood between A and B. Okay? So what is the longest possible time a passenger will have to wait for a train? If the passenger arrives just after the door closes, missing the train, they will have to wait the full 3 minutes for the next one. Okay, so B equals 3 minutes, which is 180 seconds. Okay, so there was a film a few years ago called Sliding Doors with Gwyneth Paltrow that sort of had this scenario. Anyway, so what is the probability that it'll have to wait longer than 2 minutes? Okay, so this is interesting. So the way we go about this is the probability of x greater than, let's say, k, and that is equal to b minus k, where k is the b is the upper bound, and b minus k is the range of possible values that can exceed k, divided by b minus a. So in this case, what we have here is 3 minus 2 divided by 3 minus 0, which is 1 over 3. So it's 1/3 of a probability, or sorry, the probability is 1/3, 0.33, 33% essentially. Okay. So what is the, oh, that's a mistake. What is the probability that they'd have to wait less than 45 seconds, i.e. less than 0.75 seconds? Well, in this case, something similar. The probability of x less than or equal to k equals k minus a divided by b minus a, and there we have it there, 0.75 minus 0 divided by 3. Let's just put it in there just for the sake of completion, and that is 0.75 divided by 3, that is 0.250, which is 25%. The graphic I have here is the probability density function corresponding to 0 to 3. So essentially it's enclosed in this rectangle here that I've just highlighted. So the total area of this rectangle is 1, and again the rectangle is sort of specific to the uniform distribution. The shaded area, so the upper and lower bound is 0 and 3, okay, and the shaded area corresponds to the area that's less than 0.75, okay. This is 0.75. This has an area of 0.25, which corresponds to the probability of x being less than 0.75. Okay, so on. Likewise, up here, I mentioned it here also, I should have mentioned it here, that this is 1/3 of the area of the entire rectangle, and the shaded area corresponds to the probability of x being greater than 2, okay, which is 1/3. Now, it's not really helpful in the case of the uniform distribution specifically, but it's sort of good to get used to these on an ongoing basis, particularly when you get to the normal distribution. Okay. Now, so we're going to find the mean and the variance, so the expected value of x. There's a little formula for that, and it is b plus a divided by 2. That is 3 plus 0 divided by 2, which is 1.5 minutes. Okay. The variance is b minus a squared divided by 12. That is 3 minus 0 squared divided by 12, which is 9 squared, and that is 0.75. Well, actually, you could sort of say that's minutes squared if you want, because that's the correct thing to do. That's just being rigorous. Probably too rigorous. But anyway, we'll leave it there.